Welcome to our Cognaize webinar from large language models to precise language models. Before we dive in, let's address some technical aspects. All attendees are muted to ensure clarity. We have roughly 80 registrations. Nevertheless, we highly encourage your participation through the Q&A field below. We'll address as many questions as possible, and you're also welcome to send questions directly to me for private discussion. Cognaize is at the forefront of AI solutions for the financial sector, impacting banks, rating agencies, insurances, and asset managers globally. Today, we'll navigate the challenges and benefits of AI, focusing on hallucinations and practical deployment strategies considering computational constraints. And now it's my pleasure to introduce my colleague, our founder and CPO, Vahe Andonians. A banker by trade and an AI scientist by passion, Vahe has successfully bridged the gap between finance and technology for the past 15 years. Vahe, we're eager to hear your perspective. The stage is yours.
Thank you very much. Let me just share my screen and let me know if that works.
It's still in preview mode, so you...
It's not loading?
It's good.
Good. Okay, great. Thank you very much. Yeah, welcome everyone to this webinar, and thank you for your interest. In the 1980s, the economist Robert Solow made a thought-provoking observation. You can see the computer age everywhere, but in the productivity statistics. Interestingly, we initially witnessed a decline in productivity with the advent of computers, and it took nearly a decade to regain the levels we had before their widespread use. I'm very passionate about artificial intelligence and its impact on our society. We are here committed to finding solutions so we don't experience a similar loss in productivity during this current industrial revolution. An interesting tool to achieving this is what we call precise language models. I'm thrilled to have the opportunity today to talk to you about this approach. When it comes to language models, the traditional approach has typically involved a two-stage training process. Pre-training and a fine-tuning. In the pre-training phase, models are trained on a large, diverse data set. The goal here is to help the model to learn a wide array of language patterns and structures, essentially providing it with a broad understanding of the language. Following is then a fine-tuning, and here it's trained on a more specific data set relevant to particular tasks or domain it will be used for. This phase helps the model to adapt its broad knowledge to a specific application. So the most important aspect, though, is this, that in this most important aspect is that these language models only learn during training, and they only learn through adjustments of weights, which means in inference, so when you actually use them, there is no learning happening. Now that actually changed. That's changed with what we call in-context learning. So as you might be aware, with GPT-3, the first time we saw this ability of a language model to adapt itself at inference, right? And here's an example of it. So the scientist gave it the following task, an input of 2014 0601, and wanted a specific output, which is a exclamation mark 06, exclamation mark 01, and so on, which is a non-typical task, right? So it's not a usual date format. So you would expect it not to be able to do that. But the model was actually able to do this, right? And this is called in-context learning. And this is something very, very new, right? So before, you always had to train a model so that it can actually perform a task. And here, we don't need to train a model, but we actually just give it a example or a few examples, and it is able to do these things. Now, this is actually making something very specific to humans, because now these language models have the ability to learn socially, right? They learn by prompting, they learn by context, which is something that we humans do all the time, but was very, very abstract, was not possible for a language model, right? And that is what changed. And actually, something more happened. So even more, which we call the chain of thought prompting. So what also happened is that these language models have now this ability to actually reason. And this reason is very important. It's not only important to derive to the right answer, as you can see here in this example, but it is also important because it gives you an insight on how the language model is actually solving the issue. So it creates some kind of transparency and also a way to inject your knowledge into this and then guide the language model to do these things. And this is called chain of thought prompting. And these two together obviously change everything, because before we literally always had to train and then use a model, but now you could actually add inference, train a model, and inference instruct it to behave differently. But there are, of course, problems too. And these problems can be actually very major. And the first problem is this, it's the size, right? So what you see here is the embedding models from OpenAI. You have your Ada, Babbage, Curie, and Da Vinci. And Ada starts at 350 million parameters, and then Babbage is at 1.3 billion, and then Curie is at 6.7 billion, and Da Vinci is already at 175 billion parameters. And so look at the jump, right? You jump from Curie at 6.7 billion to 175 billion, which is 2,512%, right? And at the same time, and now this chart is very interesting, you see here the number of in-context examples that it needs to actually achieve a certain accuracy, right? So you see here this Babbage, for example, needed 4 examples to achieve about 70% accuracy, right? And you can see that Ada is basically not able to do in-context learning. I mean, it gets a little bit better, but in reality, it doesn't reach even the 50%. Babbage actually converges to some value, but it takes some time. But the real interesting part here, and that part is going to be very important for today, the really important part is that Curie and Da Vinci, even though they have 2,512 percentage points difference in between them, they're almost the same, right? They almost perform at the same level. Curie is just a little bit worse than Da Vinci is, right? That's a very important observation. Now, just to put it into perspective, I was showing you only the embedding models from OpenAI. If we talk about ChatGPT, right, the 4.0, and this is just unofficial knowledge, because OpenAI has not officially released their parameter size, but supposedly it's 1.7 trillion parameters. So basically, it means in this whole world, there are only a few companies who can actually operate that, right? Who can actually deploy this and actually use this. And then you see, of course, news like this year, Microsoft targets nuclear to power AI operations, right? So this is serious energy consumptions, that much that a technology company is thinking about building its own power plants, right? And then it needs even a nuclear power plant to fulfill on this. At the same time, and I think this is really important, where we have all these great things, in context learning and chain of thought. At the same time, this is a very interesting article, and it is from December, so it's not even 1 month old. GPT and other AI models can't analyze an SEC filing, researchers find. So if you look into the article itself, it says that they tested it, and then GPT-4, which is the most advanced model currently of OpenAI, get questions only correct at only about 85%. And that is already very bad, but it actually gets worse, because if you look at this piece here, This was written after Microsoft showed their Bing AI, and on stage they asked Bing a few questions to answer about gap. And here you see what they answered. So it's a perfect screenshot of what they answered, and we have marked with overlaid over it all the mistakes that they have done there also in this article. So basically, if you look at the numbers, Bing AI got every number wrong. Like instead of 37.4%, it's actually 38.7%. The operating margin is not 5.9%, but it is 4.6%. The diluted earnings per share are not 0.42, but 0.71. And even the expected net sales is not correct. So like almost everything was wrong, right? Live demo during their release. That is, of course, the result of what we call hallucinations. So hallucinations are answers that you get from a language model that are not justified by the training data. So the training data wouldn't justify those answers, nor the data that you're injecting to it, but it comes up with this kind of data. Of course, hallucinations are not unique to computers. Very famous people have also lots of hallucinations, supposedly. But let us look at hallucinations a little bit scientifically, right? So if I tell you properties like divergent thinking or expansion of semantic activation or cognitive flexibility, or creative problem solving, all these things are actually positive aspects to advance knowledge to new things, right? So you would need creative problem solving to actually advance knowledge, right? And you would need something like an expansion of semantic activation or divergent thinking, which is several solutions for the same problem. All these properties that I just said are actually side effects of hallucinogenic drugs. Now, I'm not advocating that anybody should take drugs, but I'm looking at it a little bit scientifically, because if you think about this from a scientific perspective, what those drugs do to a human is they basically flatten what we call the brain's dynamic landscape, which means every time when we switch context in our brain, then we need to spend some energy to do that. And when you have these hallucinations, then this switching between context is very, very easy and very fast. So you're suddenly connecting things together that usually are not connected. And then sometimes, not always, but sometimes something very useful comes out of this, right? And this is the way we have to think about hallucinations, because hallucinations are actually a feature and not a bug. We, in the context of financial industry, are thinking of it as a bug, but in reality, it's a feature. And that is also, of course, manifested in lots of research. Here's a very good example. An AI that can design new proteins could help unlock new cures and materials, right? So the way these scientists have solved this is by increasing the degree of hallucination that this specific AI model was having, right? So by increasing, they actually found new solutions, new materials. And I'm very sure that you have read the recent announcements of DeepMind with finding new antibiotics, over 233,000 new materials that were unknown to humans before, and so on. All these are actually the result of what you would call hallucinations per definition, right? Because they can't be justified by the training data because they're new, so they weren't in the training data. So it needs to be an hallucination. Let me just check. I see here chat. Somebody's writing. I think there are some questions. Let me see if there's anything I should address now. Oh, no, it's not. It's just, okay.
Just me.
So for us, though, right, for the use cases that we are doing, these hallucinations and also the size of these models is a problem that needs to be addressed somehow. Before we can address it, let's just understand how these language models are trained. So I'm going to try to show everything to you very conceptually, or the essence of it, and not necessarily mathematically. Basically, all these models that we are going to talk about right now are instruct models. Instruct models are models that follow a certain pattern, and also the pattern that you would like to see in the training data, which is a user asks something as a request, AI is answering. And now, as some of you might recognize, I am using here the pattern of the GPT series, because other instruct models just have request response, whereas OpenAI is using request response, request response, request response, right? So more conversation, more context there. So to build a bot like this that can follow instructions and do something, they go through 3 steps of training. I mean, in reality, it's 4 steps. I just omitted one because the one step is really just out of economic reasons and doesn't have any effect to the point here and to the language model in itself. First, it is generative pre-training, and then it is supervised fine-tuning, and then we have a reinforcement learning from human feedback. So let's look at generative pre-training. And there it is really just a autoregressive sequence model, right? So what does it mean? It means basically, sorry, I just promised not formulas and then formula, but basically what it means is this is the history, and the history is affecting the next thing that you're going to predict, right? That's the whole idea of an autoregressive sequence model. As an example, Vahe is really, so now there's a probability distribution, and of course, I'm funny, but this model thinks with a higher probability that I'm boring. So it would choose the word boring here. And so I would continue with Vahe is really boring. And then you see there's a stop. Stop would just mean we stop the sequence and the sentence is finished. But a higher probability than stop is just. So if we adjust to it, it says Vahe is really boring, just. And the highest probability is kidding now. So the language model is actually very intelligent because, right, I am definitely not boring, right? So this is how it works. It just predicts with the highest probability what is the next word. Now, that might seem very simplistic, and then it might lead to the thought that this can't be intelligent, it can't be good, it can't be this or that because it's just a probability map. I don't want to go into this part. I just want to remind you that our whole intelligence is just based on an ion difference of sodium and potassium ions. So if intelligence cannot be a probability map, then why can an ion difference be that, right? So I think we haven't understood yet how intelligence and consciousness actually comes into place, but it's definitely a probability map would definitely be enough for that. Now, if you think that this language model at this point has been trained essentially on the whole internet, right? So it has seen a humongous amount of data. So why isn't that enough, right? You could argue, well, I mean, you've seen like almost everything that is publicly available and probably a lot that is not publicly available. So why isn't that enough? Why do I need a second and third stage of training, right? And the reason is it's an alignment issue here, because most of the data that the system has seen is not following that pattern that we have described in the beginning, right? It's not a request, reply kind of thing. And as a result, it could answer to a question like this in the following way. It could say to a user who says, how much is the gross margin, right, of whatever context we are talking about? It could say, suppose you are a businessman who owns a big construction company. The total net sale of your company is 560,000 and a cost of goods sold of 490,000. So that is not an answer to our question, but it is justified by the training data because it took it from a question summary somewhere in the internet. I actually took it from something like this, right? So there's an internet, there's a page where it says how much the gross margin, and below it gives this description, right? So that's what the language model learned. So it's not clear that it actually learns the pattern that you want it to learn. So for that, you need to train it on a subset, right? On a specific subset of it. And that subset you need to create. And that creation is happening now user communicating with a user and not with AI anymore, right? You see here it says user, but here it also says user. So a user is talking to another user, or in all reality, probably talking to him or herself, right? And then creating some kind of chat thing. And that is then used to supervise, fine-tune this model. Now these SFT models will already respond significantly, much, much better than the raw language model. But there's still a problem. And the problem that we have now is that there is a distributional shift. So what does that mean? Because when we trained it, there was a human asking the question and defining the answer and then asking again the question. Now, in the real setting, a human is asking a question and the answer is coming by AI. Now, AI has not learned the answer of a human by heart, but just approximately. So there's a small shift, right? And that small shift is unfortunately compounding. So if you look at it graphically, what you see in the middle, this dark blue spot, is what we call the policy. So that is where you want the answer to be. And the red is signifying where the answer actually was. And you see that the first time we ask something, the answer is within the policy. That's great, but it's on the edge a little bit, right? But now it's compounding. So the next answer that we give now is further away because the probability will ask it to be further away because difference is growing over time. Right? So what happens is very fast you drop out of this area that you want it to be, which is called the policy area, and it answers some weird stuff that you don't want the model to do. Now, how do we solve this? We solve this with what we call reinforcement learning from human feedback. And what we do here is we take basically the SFT model. And the SFT model is generating not one answer, but a couple of answers, right? Like in this example, you see 3 answers, right? So you give it a prompt and it gives you 3 answers, A, B, C. Okay? Now, a human or a group of humans is ranking those by their which one is the best, which one is the second best, and so on, right? So like literally ranking those. And this is the ranking here. And the ranking suggests that B is the best answer, and then is A, and then is C. Now that part, this ranking part, is taught to a model, and that model is the so-called reward model. So this reward model here is learning what the human thinks the preferences like are. Right? So why aren't you directly training the SFT model? Because the SFT model is huge, right? And you would need to do lots of examples so that you change it. Whereas the reward model is a small model. So with very few data points, you can train it. It's a trick, basically, right? You train a small model that then trains a larger model, right? So you train this model, then this trains this here, okay? Now with this, we come to this very important chart that basically decides everything. So this is a GPT chart, right? So this 175 billion was the size of GPT-3, if you remember. Now, what you see here is, so the model size, right? And these lines, the Y and X axis, are about how often, this shows how often this line is beating the SFT model. So for example, when we look at this point here, this point would say that in 0.1s, like in 10%, this model with 1.3 billion parameters is beating the 175 billion SFT model, right? Because that's the point where it's exactly 0.5. Right? So you see what 2 or 3 very important things. The first thing is SFT really helps. So this is the pre-training, and then if you do SFT, it gets significantly better, right? So it's higher. But what you also can see is that reinforcement learning with human feedback is also very important. Actually, more important, really elevates it to a new level. So this is a very important thing. And what you can also observe here, and this I think is very important for our later observations, is this, that 175 billion SFT model is worse than a 1.3 billion parameter reinforcement RLHF model, right? So only 1.3 billion parameters, if trained really with human preference, beat already a 175 billion SFT model. That is very important. So this is a very flat curve. All of those are flat curves, and that is actually important for all the decisions that you have to make later on. Now, after hearing this, it's very clear, right? The obvious solution to get rid of hallucinations and also get you know, a model that you can operate on a adequate hardware is just retrain it, right? Just retrain more data on the last level, and then you won't have any issues, because as we just established, this model, a much smaller model, is actually beating this larger model. Now, there is, of course, a couple of problems attached to it. So first, these models are really huge. And so when we say something has 1.7 trillion parameters, like let's forget 1.7 trillion parameters, right? But even if we look just at only 7 billion parameters, right? 7 billion is not much, right? Even if you look at 7 billion parameters, what does it mean? It means basically that there are lots of those calculations that you see here, where it's a summation, and then after summation, so first multiplication, then summation, and then an activation function goes forward, and then you also need to do it backwards if you want to train this model, right? So there's lots of calculations going on here, and to do these calculations, you need some space to store these values, right? So if we only talk about a Llama version 2 7 billion parameter model, which is really not large, right? In the realm of what we are used to, 1.7 trillion parameters and so on, is actually, one would say it's actually small, right? So even for that, you need 27 gigabytes of memory to just save your model parameters. You need 27 gigabytes to save your gradients, right? You need 54 gigabytes to save your optimizer states, because you're optimizing things, so that optimizes the atom or whatever needs some states, so that also needs some memory. If you sum it up, you're at 108 gigabytes. 108 gigabytes is far beyond any consumer grade hardware, right? So consumer grade hardware, let's say like a 4090 RTX or something, has 16 or 24 gigabytes, right? So it's like 5 times over this, right? So you really need already to buy some huge hardware, right? In this case, it would be already an A100 or something to be able to train even only a 7 billion parameter model. Now, this is, of course, too resource intense. So how can you solve this issue? We go back to our thing here that this curve is very flat. And obviously, we have to ask this question: do we actually need to train all the parameters, or can we just skip some of those and not train them, or take a smaller model? And here it gets very interesting, and I want to explain this concept now on the example of the attention layers. Right, you can apply it to many layers in the transformer. But I'm going to use the attention layers because they are the layers that are the most discussed about and also very applicable to this problem. So for the sake of making things easier to draw, let's assume our vector space is only 2-dimensional. So every word has a 2-dimensional vector. And we can plot this obviously in this area here. And then you see at the top right, you see an orange, and at the bottom left, you see a phone, right? So that's easy. Fruits somehow are all there, they are grouped there, and then technology is down here. But then where would you place Apple? Now, Apple can be, of course, the food, then it should be somewhere here, but it can also be the company Apple, then it should be somewhere here, right? So the question is, how do I decide this? So if it is, and that's very easy, right? If it is a sentence like "I like apples and oranges," then we know, oh, this is about fruits, and then we change this embedding of this apple that started here towards this direction of the orange. And if the sentence is something like, when it comes to phones, I prefer Apple, then we know they're talking about technology. And then we are moving this embedding down closer to here so that it clusters with this here. Right? Now, how do we do this actually? Right? And that's important. We do it, and again, I want to explain it to you intuitively rather with the formula. I mean, I'm sure that many of you or all of you know the formula behind this with a query, a key, and value. But what you actually do, and this is the interesting thing, what you actually do is you're doing some kind of linear transformation because you're doing a matrix multiplication with this. And a linear transformation to any object in a space is just a transformation. You're just skewing this, right? So basically think of, you start with this, and then you do some kind of multiplications, and you could end up in this one here, or you could end up in this one. Why are you doing this? You are doing this kind of transformation because you wanted to make it easier for these embeddings to distinguish itself, right? So you want a separation of the company Apple from the food Apple, and that separation you will achieve easier in certain transformations, right? So in this example already you can see that, because if you look at this one here, right, at this middle one here, so if this apple moves in this direction and this apple moves in this direction, they're actually not really separating from each other, right? Whereas in this picture here, they go really in opposite directions.
What?
You want to say
There's the
something?
first question actually.
Oh yeah, please.
Should I throw that in? I think that goes back to the previous slide with
Sure.
the models. The one before that. Does it make sense not to quantize if enough resources are available? So I think that's rather important for banks probably, and most of the participants are from the financial industry.
Yes. Actually, I'm going to cover this in a little bit later. So the short answer to this is I don't think it does. And if you allow me, I don't know who asked this question, but if you allow me, I will answer this at the end, because you will see that I need to build up something before I answer it, so that the answer is meaningful to you. But the short answer is, and I think it does not make sense. I think it makes sense to quantize it, but we'll get to this pretty soon.
Okay.
So here, right, when we have this transformation here, now here we see, of course, that this transformation really helps the embedding model, right? So we transformed it a little bit, and this transformation made the separation between the company Apple and the food Apple really, really. That's what we're doing right now. You can mathematically, we are doing some multiplications, but if you think of it conceptually, this is what you're doing. You're doing a transformation, and you're trying to find a transformation that would result in an easy separation of these two contexts. Now, if you look at it in a three-dimensional space, any kind of transformation can also lead to what we call a collapse, right? So here's a good example. So you see it starts as a cube, and I'm doing some transformation that after this transformation is just a pure linear transformation. After this pure linear transformation, it is not a three-dimensional space anymore, but a two-dimensional space. Now, in mathematics, we call this a rank, right? All of us have learned it in school, obviously. But the idea is very simple. Is there any vertical vector in a matrix that can be the combination of two others? And if that's the case, then automatically there is some kind of transformation that would result in a loss of dimension, right? So you lower the rank of it. Now, that's very important, because if you can lower the rank, it means that that column actually doesn't play a role, or at least not a major role, right? What we need to find out is, do we have such kinds of lower rank matrices in our weights or in our attentions, or not. If we would have these things, then it also means that we actually don't need to train all these parameters, because some of them are actually useless, right? And that is the case, as Microsoft has shown with their research. Before I show you that research, what you actually would do then in such a case is you can decompose a matrix to two smaller matrices, right? So if you take this matrix here, it has 1024 columns, 1024 rows, so a lot of cells here. But if I take A and B, which have only 1024 and 384, and then 384 and 1024, the multiplication of these two will, as we all know, result back to this one here. So it will be a 1024 times 1024, but the weights that are the numbers that I have to save here are less than here. Now, I can only do this without a loss if and only if the rank of my matrix is lower than the number of columns, which means that there is lots of things in my columns that actually really don't matter. And that is what Microsoft found out in their research, which is called low-rank adaptation of LLMs. And what they suggested in their research is, rather than looking at query key value here and training it fully, you could actually decompose the matrix, fix a part of those, like one of these two matrices that you create are fixed, you're not adapting it, and just train the other one. So now you're reducing your 7 billion effort to a much smaller effort, right? And you are not losing much. Why? Because the rank of these matrices is not equal to their number of columns. Now, can you apply this only to the attention layer? No, of course not. You can apply this to other things too. I mean, you could, of course, do a full model fine-tuning, but more common is what we call adapter modules. So adapter modules are modules that you're specifically training, you're putting somewhere either in the middle of your language model or at the end of it, right? So there could be an adapter for ethical values. There could be an adapter for certain types of language, like legal language or financial language, right? And then another way of fine-tuning these models is also what we call layer freezing, where you just freeze a certain amount of layers and say, like, this I'm not adapting and I'm only changing these last layers or the first layers, right? So you can do that in your training. Now, one more thing, I promise, it's just one more thing. And I want to go back to this chart where I said it's 27 gigabytes plus 27 gigabytes and plus 54 gigabytes, and it's 108 gigabytes. And then, but I never told you why. Why do I know it's 27 gigabytes, right? I mean, you could ask, you could say, well, this, that I'm not right. And I can prove you that I'm right, because all these weights that you are using in these matrices are essentially floating point numbers. And these floating point numbers have to be stored in a computer in a certain way. And the way they're stored is they're separated in mantissa and exponent, and either stored as a 16-bit or even a 32-bit number, where one is used as a sign, so this is negative or positive, and then you have an exponent, and then you have this mantissa. So this 16 bits at the very least is used for these weights. Now, if I look at these weights in a histogram, like a distribution of these weights, then I will see something like this, right? I will see something like this at the top, which is at full precision. I'm picking like every value that I've seen for a weight in there. So it has somewhere a maximum and then somewhere a minimum. And then around 0, it is probably the highest number. Now, what I can do with this is I could actually say, rather than storing this at full precision, I can build clusters of it, right? So I could say a thing that goes from the smallest possible number to this number here is actually only this number for me. And everything that is higher than this number to all the way to eternity is this number. And in between, I can do the same, right? I can say like this thing here in the middle, every number that is here in the middle, I just store this number. So what's the advantage of this? The advantage is you're dealing with much less numbers, right? And oftentimes you're not using much, actually. Now, if you do it in a more intelligent way, so this, what I just showed you was a linear quantization. So if you do it in a more intelligent way, which is do the quantization only on those areas where the values actually really don't matter, right? And they really matter at the edges more than they matter in the middle. Why? Because of the activation function that you're using. So then you would say, oh, at the end, I keep it at full precision, but in the middle, I do a quantization, and then I don't lose anything except I have more memory. I need less memory space to do my calculations, right? And if you look at it in a graphical representation, it would mean you take the smallest value that you have in an ABS max quantization, the smallest value that you have, map it to minus 127. Why 127? Because that's 2 to the power of 7, the 1 bit we need for the sign. And here you do the same thing, the largest number here, and then somewhere the 0 point results at something, right? You will also do a little bit of a different type of quantization, which is called the 0 point quantization, where here you try to keep the 0 point in the middle through a certain operation here, but I promised not to show mathematics. Now, if we put everything together, the world gets very, very beautiful suddenly, because what we have seen is the following. We can take a language model and we can train it. And even if we take a 7 billion, even if we take a 70 billion parameter language model, we essentially, because of these low rank matrices in the attention layer, and by the way, also in some other weight layers, we can train only a certain portion of this and not lose anything. Plus, we can quantize it, meaning that we can represent these numbers in even smaller numbers. And in the end, we end up with a model that is better, faster, cheaper, and private, right? So what does it mean? It means it will be more accurate than the generic model. It will be faster because you are not using, difficult floating point operations, but integer operations. It will be cheaper because you don't need a fancy hardware. Factually, you can even run these language models on your computer now. I'm sure you have heard of GPT-4o, or you have heard of LM Studio, or my favorite is actually Olama. These are all tools that give you access to quantized models that you can download on your computer and then use them basically on your computer. Right? As the last thing, I want to actually answer this question, and that is it like, would you quantize if, I think the question was, would you quantize if you don't need to because you have enough resources without quantizing? And my answer was yes. And this chart explains why my answer is yes. Because I think that the future of AI is going towards a method of several predictions and then having a verifier choosing the right prediction. So you ask a model to not give you one right answer, but to give you 100 possible answers, or 1,000 possible answers, or 10,000 possible answers. And then you have a verifier that chooses the right answer of this. And even if you don't do that, you definitely will do what is called a mixture of experts, where you have a couple of models that are different, working towards the same goal. Either way, you are doing at inference more models than we are used to. And if you're doing more models, then you will need that space. So it's good practice to start already with a quantized model, so that I don't have this issue that I cannot run them because then they get too large, right? And this chart exemplifies this in a very good manner, because what this chart shows you is, so this is from OpenAI, and what they have done is the following thing. They have used a language to mathematics data set. So basically, there are mathematical questions in this data set, and then asked AI to answer it. So as you know, probably know, that AI is pretty bad at mathematics. So it is their goal to make this better. And the tactic that they're using is interesting, because the tactic that they're using is they're asking the same model not to answer the question once, but, and you see it here at the bottom, to answer this question 100 times at this point, 1,000 times at this point, right? So they're saying, answer the same question 1,000 times. And then they're training a verifier, and that verifier is then choosing the right answer out of those answers, right? Now, you can do it in two ways. You can have something which is called outcome supervised. So you're just looking for the answer to be correct, but you're not looking at the process to find the answer. So was the process correct? And the other way is, of course, you can look at the process, which is called here in this chart PRM. And what you can see here is that if you train the verifier to favor solutions where the process is right, not necessarily only the outcome is right, then it achieves levels of accuracy that were unseen before from a language model. So this is one tactic, and there are other tactics, but in the recent couple of months, every tactic that we're seeing goes through running more models, right? Being agents, being a mixture of experts, being this verifier pattern. All of these actually require more models to run an inference. That's the reason why I think you should definitely quantize it. With this, I'm stopping here. Any questions that I can answer?
Great. Thank you very much. So there are two more questions so far. How much data does one need for the supervised fine-tuning and reinforcement learning with human feedback?
Yeah, that's the most liked question by any business leader, because that obviously costs money. So you need to know how much. At the same time, it's a very difficult question to answer, because there are many parameters, right? So of course it depends on the model size, and then it depends on the problem that you're trying to solve, and then it depends on the variability of your data, because just the same data a million times doesn't help you. So it depends on many factors. But I can tell you one thing, that a modern setup doesn't actually need that question to be answered, because in a modern setup, and some of our clients are doing, exactly this. We're fortunate enough to help them in achieving this. But what we're doing there is creating this data as a byproduct, right? At least for the SFT stage. You cannot do it for the human preference stage, because there you basically need to await what the result is going to be. So that is a manual effort. But for the first, you can actually collect lots of data. So the question is, do you have a pipeline that makes sure that any kind of business extraction that you're already doing also has this training data as a byproduct? And if you have, then this question of how much data you need is not going to be a burning issue for you. Whereas if you don't have that, then you literally need to go back and label data, and that will be, could be expensive at least.
Thank you. One more question that I find here that goes more into the field of regulation. unique challenges in applying language models to regulated industries like finance, and how does Cognaize help address these challenges for their clients?
Look, I mean, language models, as you probably all know, are not necessarily answering the same if you ask the same question twice, right? And that's always a problem. So if you ask the same question twice, it might hallucinate, but even if it doesn't hallucinate, it has a probability distribution, and there is a factor which is called temperature. And even if you set the temperature to 0, there is still a probability left that it comes up with a different answer, or at least saying it differently. It might say the same thing, but it might say it differently. So as soon as you have a framework like this, it's obviously difficult to double check, right? Was it correct or not? Because it suddenly you might need humans to do that. So there are strategies for that. One of the strategies that we are implementing is, having larger language models train smaller language models. So the larger language model is perfectly able to answer this question that the small language model is trying to learn. So you can use actually the large language model to verify if the small language model is right or not. That is also from a regulatory perspective preferable than not checking it, obviously. So even if AI checks it, and that is something that we are already doing a lot, right? Because essentially any kind of simulation that a bank does is built on other values that probably also, or some of those also have been simulated. So it is basically not a from a regulatory perspective, not a problem. And I think that being in a regulatory space makes things, of course, more difficult, much more difficult. But at the same time, it also creates an opportunity. I think that if we look at a regulation from the angle of it could be an opportunity because it is hard to innovate in such a space, means that not everybody will be able to innovate, which then means that if you are able, you are creating some advantage to it, right? So it creates some kind of separation. And I think if you look at it from that perspective, it's very clear what you need to do, right? Which is doing this kind of innovations alongside with this regulation. I think the major problem with regulation is often that they are not clear what they want. I think with AI, though, especially if you look at Europe, I mean, the US is not regulated anyway, but in Europe, the regulation actually, I mean, the draft thing that needs to be translated now into law actually makes a lot of sense. So if in contrast to GDPR, this one I think is not very bad, and it wouldn't limit much of the things that a bank would anyway do. So I think that should be manageable.
Yeah, I think, and it's a good point. I mean, we are also sitting and working with a German standardization organization, the Dean, and they are currently trying to put something in place
Exactly,
based on the
right?
EU guidelines. It's difficult at the pace of innovation that we are facing to really address this topic.
Yeah.
Great. Thank you very much, Vahe. I think there are no other questions.
Great.
With this, I'd like to thank everyone for joining us today. Your participation and insights have greatly enriched this discussion. If you have specific questions or are interested in a personalized demo, please do not hesitate to reach out to us. We will be sharing the recording to the session in the next few days, along with some additional resources. And we also very much welcome your feedback, as it helps us to create even more valuable experiences in the future. Keep an eye out for our upcoming webinars and events. We look forward to continuing this conversation and exploring new frontiers in AI together. Thank you once again, and have a great day. Thank you, Vahe, for your time.
Thank you. Thank you.